Welcome back, young students of chemistry. This lecture is on something called photoelectron spectroscopy, and this really is the evidence that we have to support our modern model of the atom, the model that involves energy levels and shells and subshells and so on. So first we're going to talk just a little bit about the historical models, just a little reminder here, and then we'll talk about ionization energies and what they have to do with photoelectron spectroscopy. And then finally we will look at the data and what the data tell us about our modern model of the atom and how we used that data to come up with that model of the atom. So first of all, remember that we started off with Dalton, and Dalton was using much of his own work as well as works of others to come up with the fact that when elements combine, they combine in simple whole number ratios. And he developed his theory of the atom, which says atoms are indivisible and there's nothing smaller than an atom. And he was a big contributor with his law of definite proportions. And then came along Thomson, who was using a cathode ray tube, and he was able to use some ratios and determine the negative charge in the electron as well as the charge to mass ratio. And then came Rutherford, and Rutherford was actually a student of Thomson's, and he was using the gold foil experiment to determine, and he determined that there is a nucleus in the atom, that all of the positive charge is actually in the center of the atom and the electrons are outside. And then of course we had Bohr, who had a great mathematical model with the bright line spectrums from hot glowing gases. And he said, hey, I can predict what I'm going to see here in terms of the wavelength of light that's coming out of the atom. And that worked really great for hydrogen, but unfortunately it fell apart when we were talking about atoms that were other than hydrogen, which there's what now, 116 of them. So how do we know that our modern model has some relevance? First of all, we start with Bohr's observations, which are significant. If you put energy in, an electron will move from a core position to a valence position, or from a lower energy level to a higher energy level. And as it falls back down, it will release that. And we can observe that as a particular color of light. We can even calculate the energy involved with that light using Bohr's equation if we're talking about hydrogen. Another proof that we would have towards our modern model is the look at successive ionization energies. If you look at this chart, we can see that if you consider magnesium's first ionization energy versus its second, it takes more energy to remove that second electron from magnesium. And that's because in order to remove the second electron, we also have to remove the first. So the total amount of ionization, the total amount of energy that's needed to remove 2 electrons is actually 735 plus 1,445. I'm assuming this is in megajoules per mole, which is going to be 2,180. I'm assuming again, megajoules per mole, to remove the first 2 electrons. And notice that that is true for other elements. So it doesn't matter if we're talking about the electrons from an S sublevel or a P level, it always takes more energy to remove successive electrons. So, every time you remove an electron, it gets harder to remove another one. So we can see that these ionization energies increase for every single one of these elements as we remove an electron. However, we have a little bit more evidence here when we talk about core versus valence electrons. If you look at these numbers here, you can see that the transition from the amount of energy needed to remove the second electron of sodium compared to the first electron of sodium is almost 9 times the amount of energy. And then if you're looking at magnesium, to get that third electron, when compared to the second, you're looking at almost 5 times, or a little bit more than 5 times the amount of energy. So when you have these large jumps, these jumps in energy that are required to remove an electron. This is where we have transitioned from valence electrons into core electrons. So we know that sodium has one valence electron. The evidence is that in order to remove electron number 2, we need 5 times the amount of energy, which indicates that that second electron is in a very stable position around its nucleus. Same thing for aluminum. Its first 3 electrons, relatively easy to move. You get to that 4th electron, and you're looking at a 5 or 6-fold difference in how much energy is needed to remove the electron. So ionization energies give us some more evidence to tell us, hey, these electrons aren't the same. They're not moving in, these orbits that Bohr is talking about. So we can even look a little bit further into the atom of core electrons versus valence electrons if we consider how much energy is needed to remove a core electron versus a valence electron. We can see here that this diagram is for an atom of sodium, and if we remove a valence electron, we can calculate the amount of energy needed there using Planck's constant, and we can see that that falls in the range of ultraviolet radiation. Ultraviolet light is all around us. So this is happening all the time as we are moving through our daily lives. Electrons in their valence shell are being removed from their atoms. However, if we look at a core electron, that one there that's closer to the nucleus, and calculate the amount of energy that's needed there, if we calculate the wavelength, or the velocity or the frequency of that energy, we can see that we need a much, much larger amount in terms of kilojoules per mole. And that falls into an X-ray segment of the electromagnetic spectrum. So we can X-ray atoms, and that will make the core electrons go away. Energy in, second energy in. Now here's the thing, if we remember that if we're going to put enough energy into an atom to remove that second electron, whether it's valence or core, it's also going to have enough energy to remove the first electron. So what we need to know here is, hey, is this energy that we're putting in removing the first electron, or is it removing the second electron? And we can determine that by looking at the velocity of the electron that's coming out. Certainly an electron that's easier to remove, if we put enough energy in there, it's going to come out faster than the second electron, which needs more energy to remove it. And that would come out slower. And that really is the basis of the tool that we use for photoelectron spectroscopy. So any frequency of light that is strong enough to remove an electron from the valence shell will also, or from the first shell, will also remove things from the valence shell. Okay, so you can see here that any amount of light that has enough energy to remove electrons from the first shell can remove electrons from the outer shells, and that's where the velocity comes in. So we know that energy is equal to kinetic energy plus the ionization energy. So you're going to have this electron which you can bump off, and the energy needed to bump the electron off is the ionization energy. But if it starts to move beyond that, well, the kinetic energy, the speed of that particle, is going to give us a little bit of information about how much extra energy we gave that electron. So this is the actual tool that is used for photoelectron spectroscopy. It looks a little complicated. But there's this silver drum that has a magnetic field in it. The atoms come down through the chamber in the middle where they are X-rayed, which will knock the electron off, and that flies through the tube and into the drum. And that drum is able to detect the speed of the electron as it comes off of its atom. So that's the drum. where the electron will circle around, and we can calculate the velocity of the electron. So this is kind of how it works. This is a great little analyzer. So the X-ray or the ultraviolet source will come in, zap an electron out, and that creates this data in terms of binding energy. Binding energy is the energy that holds the electron to the nucleus. However, we're measuring that by measuring the energy needed to remove the electron from its atom and kind of break that attraction between the nucleus. So you can see this is taking an atom of probably aluminum, maybe boron it's boron with 3 protons. And you can see that as more and more electrons are being removed from the inner shell, you can see that this boron has 2 electrons in its inner shell and that 1 valence electron in the outer shell. So up in the corner here with the binding energy, we have the energy versus the relative number of electrons that are coming off. That's what those spikes tell us. They tell us that if you look at this, there are twice as many electrons coming off with the binding energy of 6.26 as there are with the binding energy of 0.52. So 0.52 would represent the valence electrons, whereas 6.26 would represent those core electrons. And that would be the twice as many core electrons as there are valence electrons. And that gives us some information about the energy levels of the electron. So that first energy level has 2 electrons. That would be the one that corresponds to the 6.26 binding energy. And the second one has just 1 electron comparatively at the 0.52 binding energy. So this is kind of how this works. You have this is inside that drum of the tool, and you can see that there's a potential difference here which creates a magnetic field. As the electron comes flying off, it will circle around the field and we can measure the velocity of it. If the velocity is what we can see there with the voltage, just some information there about an electron volt and how we can determine voltage across that potential difference there of the slightly negative plate versus the negative voltage hemisphere. So if the electron is coming out too fast, we've supplied enough energy, we're not going to be able to detect it because it's going to crash into the upper wall. If the electron comes out too slow, it's going to crash into the lower wall. So when we get the voltage just right and the energy that the electron is giving off, it will circle around this sphere and we'll be able to measure the binding energy. So here's boron with its 5 protons and its 5 electrons, 2 in the inner shell, 3 in the outer shell. If you think about what you're going to see of the data, we should have 1 spike that is a larger amount of binding energy, and we should have another spike that is a lower amount of binding energy. And then you might expect that because there's 3 electrons in that outer shell, that lower spike is going to be 3 times this, and there's 2 electrons in the inner shell, that the lower energy spike is going to be 3 halves, like 1.5 times bigger than the spike for the core electrons in that higher energy level. So let's see here. X-rays coming in. As the electrons fly through there, we can measure the binding energy. 19.3 represents a very high binding energy. So those are the ones we're talking about, the electrons that are closer to the core, closer to the nucleus. Oh, look at that. Instead of having just 2 peaks, well, now we're looking at 3 peaks. So we expected we expected that we would have 2 peaks, and one of those peaks would be about 1.5 times bigger. So this is where the data comes in that leads to our energy level versus sublevel model of the atom, where we have energy levels, and within those energy levels we have sublevels. So we have S sublevels and P sublevels, and this is the data right here. So what they're saying is that this that the boron, where it's the 19.3 binding energy, that these are the core electrons, and look at that. This 1.36 binding energy, notice that the relative height of the peaks are the same. So it's the same number of electrons that are in the energy level at 19.3 binding energy as it is in the 1.36 binding energy. And then there's about 1/3 of that height. So about 1/3 of the electrons, or 1/2, maybe that really is about half the size of the other peak at the 0.8. So this is where we get our shells and subshells from. The 19.3 would correspond with the 1s sublevel with 2 electrons. Notice the height does not change as we go to the 1.36 binding energy. That would be the 2s with 2 electrons. And then after the 2s comes this other subshell, 2p, with just 1 electron in it. So this is the evidence that we have for our subshells and our energy levels with subshell modern model of the atom for our quantum numbers. So if we analyze the data, we can see that what they're showing here is that where the binding energy is highest, like here by the 90 or the 84, those are the electrons that are closest to the proton, closest to the nucleus. The energy level, the binding energy out here closer to 0 would be those that are in the much farther from the nucleus in the highest energy level, or the valence state. So those that are closer to the nucleus are those core electrons, and the valence electrons are further out. And the peak height, the height tells us the relative number of electrons, and you can see that here, this is really cleaned up data, but you can see for the 84 megajoules per mole and the 4.7, they're showing 2 blocks, whereas for the 2 binding energy, the 2 megajoules per mole, 1, 2, 3, 4, 5, 6 blocks. So this has 2 electrons in the 1s, 2 electrons in the 2s, and 6 electrons in the 2p. We know that it's 6 because that height is about 3 times the height for the 1s block. The data is generally not this clean. We've really cleaned it up for you in this presentation. So one question you might be asked to answer about this would be, hey, what's the following element might have this spectrum? So which element would have 2 electrons in the 1s, 2 in the 2s, and 6 in the 2p? And if you consider that on your periodic table, of course, that's neon. So if we look at this one, we can see that we have 1, 2, 3 peaks that all have the relatively the same number of electrons in it. One at a very high binding energy, that would be our 1s. And then the 12.1 would be our 2s. The 7.9 would be our 2p, and it's got relatively 3 times the amount of electrons in it as the 1.51 and the 12.1. So that would be our 2p6. And then we'd have 3s2, and then 3p is half that height, so that's going to be our 3p1. So we can analyze this and figure out how many electrons are in this. We identify the electron by its electron configuration. 1s2, 2s2, 2p6, 3s2, 3p1. then we could look at our periodic table and know that that is aluminum with its 6, 7, 8, 9, 10, 11 electrons. So these are the sample questions that you would, these are sample questions that were provided from the College Board regarding the photoelectron spectroscopy data. And these are the kinds of questions you're going to be expected to answer. So again, looking at the photoelectron spectroscopy data, you'll be expected to identify substances. One thing I will tell you to be careful with is to figure out where your zero is, because that would be farther away from the nucleus of the atom. And sometimes they have the zero to the left of this diagram. Sometimes they have it to the right. So the binding energy here, the nucleus is to the left, and this would be 1s, 1, 2, 3, 1s2, 2s2, and then this is 2p, and this is 1, that's 2 electrons, so we'd have 2p, 1, 2, 2p3, and that would correspond to nitrogen. So remember, you're doing a relative height. Find your smallest one, figure out how many electrons are there, and then you'll do a relative height comparison. We know that there are 2 electrons in the 1s, and on this diagram, that's taking up 4 lines. So if we have 1, 2, 3, 4, 5, 6 lines on the very last peak, then we know, 6 divided by 4 is what? Something I can't do. Yeah, 3 halves. So it's a 3-to-2 ratio. Okay, so another example question would be, to analyze the spectra and ask things like this is asking you to explain the relative positioning and the intensity of the 2 peaks. So here's the thing, we have intensity for lithium and for beryllium. We can see that for lithium, its binding energy is, let's see, there's 0, so that's valence. So its binding energy is between 4 and 6 megajoules per mole, whereas beryllium's binding energy is between 10 and 12 megajoules per mole. And we can look at the relative number of protons in the nucleus to determine the strength of those binding energies. Lithium with its 2 protons, whereas beryllium having 4 protons, beryllium is going to hold those electrons a little bit tighter, and therefore its binding energy is going to be higher. And we can see that the peak of lithium is also 1/2 of the relative size of the peak of beryllium, which means beryllium has twice as many electrons in that first subshell as lithium does. So when we look at the question, they're asking you to pick a multiple choice answer, which is the best answer. And based on the explanation given earlier, beryllium has a greater nuclear charge, and therefore a greater nuclear charge, and it has more electrons in the 2s orbital. More data, because given the photoelectron spectrum above for phosphorus and sulfur, which of the following best explains the 2p peak for sulfur is further to the left than the 2p peak for sulfur. So again, some more comparisons that they would have you make. I'll let you take a minute to look at that. You might want to pause and think about that for a little bit. So sulfur having more protons in the nucleus will have a greater effective nuclear charge than phosphorus. and the 3p sublevel of sulfur has greater electron repulsions. The more electrons there are in that orbital, the more repulsion there's going to be, and that's going to decrease the binding energy slightly. I'll let you get a look at this. So this is more, I think, of a free response type question here, where they would ask you to explain something. Actually, nope, still multiple choice. So think about the answers. Maybe pause and think about it and see if you can answer them based on the information you've provided. And again. Okay, so I hope that these make some sense to you. I'm going to stop this here and let you work on your photoemission spectroscopy data, or I'm sorry, problem set, and then you can ask me questions in class. Thanks.